Hey everybody, Mr. Bells again. We're going to finally introduce today, this is lesson 6-3, introduce this thing called a logarithm. Again, we're not going to necessarily go into how I'm going to use logarithms yet to solve bizarre exponential equations or more crazy ones, because we haven't gotten to things called log laws yet. But I am going to show you how they're related to each other and the conversion between an exponential equation and a logarithmic equation, and that will be helpful for us as we move forward in terms of being able to deal with the algebra that involves it. So here we go. First off, again, basic stuff. Here is what a log equation looks like and how we do some conversions. So first off, don't get scared by the word logarithm just because it's you haven't heard it for a while, but LOG is its abbreviation, and you can see on your calculators, we'll use this calculator this time, there's an LOG button right here, and then this one right here, an LN, that's going to be a special type of logarithm. So these two buttons we're going to use when we're dealing with logarithms. Now, some of the calculators, when you turn it on, if you go into math, it has a special button called log base, which you can use to be able to do some logarithms. Notice this was letter A on this. So if you hit just your math key, you don't see it originally, you can either scroll all the way down to get to it. Or what I usually do is I just scroll up, and then it gets to me a little faster because it starts at the bottom and rotates back up again. Okay. So first off, what does it mean? So this is log base 2 of the number 16, and we say that it equals 4. Well, what does that mean? It means that this little thing right here is the base, and this thing over here is the exponent, and that if I do this base to its answer, the exponent, the answer of the logarithm or the exponent, it should equal this number. And you guys know that 2 to the 4th equals 16. So there's our conversion. So then this would say log base 5 of 25 equals 2. And what does it mean exponentially? Well, it means this base, right, to this power, 5 to the 2nd power, equals 25. Now, got it. So what happens here? Well, now I've got an answer of this logarithm that's -2. So, ooh, that's weird. But again, base is 6, so 6 to the -2 power does equal 1 over 36, because you know 6 squared is 36, right? And a negative exponent puts the number in the denominator. Okay, so 6 to the -2 equals 1 over 36. I can show you that quickly on the calculator here. 6 raised to the -2 power, enter, you get that as a decimal, but you're like, hey, well, what is that? Well, math frac, number 1, you can see that it is 1/36th. So it's not like we're not getting the right stuff on it. Okay, so, but if I put in, let's show you right now, if I put in the log of 16 and hit enter, it doesn't give me 4. If I put in the log of 25, it doesn't give me 2. And if I put in the log of 1/36, log of 1 divided by 36, it doesn't give me -2. So it's like, well, what good is this log button on here, right here, if it's not working for me? So what happens when I hit log of 1,000? Log of 1,000. I wonder if I can figure out what the calculator's actually doing. So log of 1,000, it says that that answer is supposed to be 3. Like, well, what? So if the log of 1,000 equals 3, then what is the calculator doing every time with that number when I didn't hit it, right? Because when I hit all those logs before, I didn't put in a base of 2, a base of 5, or a base of 6. So what would this number be? Well, let's write it over here. Let's assume that we don't know what this number is. Then that would be x to the 3rd power equals 1,000. So what to the 3rd power equals 1,000? You know that x must equal then 10. I'd cube root both sides, right? So awesome. So that means that every time that I push the log button on the calculator, so if I do the log of, say, 80 on my calculator, it's going to have an implied base of 10 when it gives you the answer, okay? So right there, if there's no base written, in the problem, if there's nothing written, it's implied to be base 10. Now, I can go into a long detail drawn out on some stuff, but basically, we use base 10 because we're humans, and humans were born with 5 appendages on each hand. So we have a number system, and then our entire number system is just 10 digits, right? The numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And there's no other numbers in our number system, just combinations of those 10 things. So base 10 is what we deal with. I'll give you another quick little thing. Base 2 is what computers deal with. The only thing that a computer knows is ones and zeros, right? Or combinations of ones and zeros, and that's called binary code. Binary code. Good deal. It just knows, is the circuit on, is the circuit off, what's the heck's going on with it. So kind of similarities between these things, and like I said, I could go into a lot more detail, but I don't want this video to be all about that. If you have more interest in it, go take a look online at something else. So how does this work out? So we need to be able to convert any logarithmic equation, if I have the log of something with a certain base equaling something, that it has an equivalent exponential equation. And I will tell you every time, if you simply start with your base and you raise it to its answer, you should end up with that. So base to the power on the other side equals that. Okay? Now these two functions happen to be inverses of each other. Inverses of each other. And an inverse simply means it undoes it, right? Like addition and subtraction undo each other's. Multiplication and division undo each other, right? Like multiplying by 5, dividing by 5. They undo what's going on. X squared and square roots, so powers and radicals, undo each other. You'd even know if you went back, tan of x and tan inverse of x, if you want to do with some trigonometry stuff, those undo each other's. Ooh, look, I even said that word, right? Inverse. And when you get to data B, you'll even talk about inverses of these things called matrices that help undo them. Okay? So these two things are inverses of each other, and they help undo them. Now we're going to look at some other things, and I'll come back to this a little bit later on. So what happens when I have the log of a number with a certain base, a special base? Oh, E, that's the thing that we talked about before. So we don't ever write this. Good deal. We don't ever write a log with a base of E, because the base of E, that, you know, E is that special number that occurs in compounded situations, things that happen continuously. So instead of writing a log of E, we use a special logarithm called a ln. But an ln, it's kind of weird, stands for a natural log. Okay? Back up here, this base of 10, right up here, that's called a common log, because it's the most common one, because again, humans have 10 fingers and 10 toes, so that's called a common log. A natural log is a base of E, so we use these letters ln. So if I don't have it written, that's what it's doing. So on my calculator, watch, here we go. So I'm going to do an ln of 18, and you can see that it gives me that number, 2.89. Well, we said, well, the implied base is E, so let's try this out. So I'm going to do E, that's our implied base, raised to the answer of that problem. Second function, answer. You guys know how to do that, right? This little ANS key pulls up your last answer. You just got to use second function and the ANS key. And I'm going to hit enter, and look, I get 18. Okay? So again, when I just hit the log button, it's an implied base 10. When I hit a natural log button, it's an implied base of E. Okay, so how do some of these things work out when I'm doing weirder stuff? And how do things kind of like knock each other off. So here, if I raise 8 to the log base 8 of x, that's going to equal x, because these things knock each other out or kill each other off, because they're their own bases. Just like over here, if I raise e to the natural log of 6, there's an implied little base of e, and those two things are just going to knock each other out. So that's going to be 6. So if you see problems like that, that's what we're looking at for it. You can even show you on this. Watch. So let's do one of these. So let's do e raised to the natural log of 4.2568. So, that'd have to be pretty weird. And watch. I get 4.2568 because e to the ln knocks each other off. The same way that the natural log of e, if I raise that to the first power, like that, then that's going to equal 1, that those two things undo each other. Okay, good deal. And that's going to be a critical part of some stuff we do later. So the last thing that I want to do is I want to show you what the graphs of these two things look like. First off, we're going to graph y equals 2 to the x, so have your graphing calculator out. So I'm going to go to y equals, I'm going to clear out the old stuff, and I'm going to go 2 raised to the x. So remember, this is an exponential function. This is an exponential function. It's going to grow big. And I'm going to hit the graph, and you can see that it looks just like that. Yeah? Whoosh. And now I'm going to go ahead and put this one in. I'm going to graph the log of log base 2 of x. Log base 2 of x. So I have to do this, right? I have to go math and then find this log base right there, that thing, 2 of x. Now the older calculators don't have that little special base for it, but I can show you how to get that another way in a little bit. So here we go. So I believe when I hit graph, watch what happens. You can see that these two things look like they are, watch this, you see this line? Put a line right there. Watch this line, y equals, I'm going to do one more, y equals x, I'm going to graph that. That these two things look like they're almost reflection images of each other, and I'm going to do a square on this, so zoom 5. So there's the first one, there's the second one, and here's y is equal to x. They look like they're perfect reflection images of each other over the y equals x. So let me kind of show you what makes something an inverse. So if I go to my table setup, I'm going to start it at 0 and go up by 1, just like that. You'll see that when x is 0 on the first function, 2 to the 0 power is 1. Awesome. But when x is 0 on this one, then there's no y value at all. There's an error there. And the reason why there's an error there, let me show you here. Okay, so this one looks like this, right? And this one looks like this. And they are inverses of each other. And when x is 0, that's right here, you can see that there's an asymptote, so it can't exist right there. So I can never take a logarithm of, regardless of the base, of 0, because there's 2 to nothing, right? 2 to no power ever gets me 0. You can see that over here, they're inverses, right? There's no x that I can do, even if it's negative of infinity, that it's ever going to equal 0. It's just going to get really close to it. Okay? So, next, looking back at this, you can see on this one that if I plug in a 2, I get out a 4, but then on the second one, if I plug in a 4, I get out a 2. See how it kind of undoes that? I plug in a 3, I get an 8. Watch on this one now. If I plugged in an 8, I get a 3 on the second one. So those two things undo each other. They are inverses of each other for these graphs. So if I had this point right here, I'm just making this up, if I had 4 was my x, right? I would get 16, saying that that's that point. Then, that's my x and that's my y. Then over here, it would look like this. That 16 way out here would get me a 4. Which, let's do this one. Just give me one more thing on this. But if I took a really, really big number, say like 8, and you can see that I'm going to take an 8 gives me a 256, right? 8 gives me a 256. That's way up there, right? That's so far up there I can't even go there. If 8 gives me 256, then over here, if I go way out here, 256 should give me 8. That is not going to grow very high. And it's this ability for us with logarithms to take, again, logarithms to take really, really big numbers and convert them to much smaller numbers in the way they work, which allows us to do things like the Richter scale. The Richter scale takes very, very powerful earthquakes and says, hey, we're going to convert them to this other number. So we're going to take something that might have a whole lot of force and convert it to a number that makes more sense. That's also true in things called decibels. Decibels. Sound intensity changes it to something much lower number. And we will look at this stuff and the use of logarithms, as well as how to use logarithms to solve later on. We can't do everything at once. Hopefully that was beneficial for you, at least a good start on it. Awesome. This is Mr. Bell's introduction to logarithms and how they work out. Inverses of exponentials, right? If you use the log button on your calculator, it's implied to be base 10. If you use the ln button on your calculator, it's implied to be base e. Practice the online homework. Get to it. Do it yourself. You'll learn stuff. Thanks. See ya.